Welcome to finding integrating factors in two variables. So recall previously we assumed that our integrating factor mu of xy took the function of x, p of x, times q of y, using capital P and capital Q. And then we got that this therefore meant that my minus nx was equal to p prime of x over p of x times n minus q prime of y over q of y times m. And so let's just go ahead and rewrite that. As my minus nx is equal to a lowercase p of x times n minus a lowercase q of y times n. Then lowercase p of x is p prime of x over p of x. Lowercase q of y is q prime of y over q of y. We can get our capital P of x and capital Q of y, therefore, by integrating. And so we get a fact from this. It turns out if my minus nx can be written in the form lowercase p of x times n minus lowercase q of y times m, then mu of xy equaling capital P of x times capital Q of y, where capital P of x is e to the integral of lowercase p of x dx, and capital Q of y is e to the integral of lowercase q of y dy. This works as an integrating factor. So the trick is being able to find our lowercase p of x and lowercase q of y functions that will make that fact hold true. So let's go ahead and just work through an example. Let's consider the equation 2y dx plus 3 times, in parentheses, x squared plus x squared y cubed dy is equal to 0. So first, let's just make sure the equation is not exact to start with. So our m here is 2y. So my is 2. And I'm going to write in the format 3x squared plus 3x squared y cubed. And my screen's not updating. One moment. Trying again. So we had m was 2y, therefore the partial with respect to y of m is just 2. And if we distribute our 3 is 3x squared plus 3x squared y cubed. So that its partial with respect to x should be 6x plus 6x y cubed. So these are clearly not equal to each other, and so it's not exact. From here, we need to find an integrating factor. I can tell you right off the bat that if we look at my minus nx over n is not a function of x. Similarly, nx minus my over m is not a function of y. So our last option is to try writing my minus nx as some lowercase p of x times capital N minus some lowercase q of y times m. So my minus nx, we are looking at 2 minus 6x plus 6xy cubed. And on the right, we are looking at p of x times 3x squared plus 3x squared y cubed minus q of y times 2y. So our left-hand side, we have 2 minus 6x minus 6xy cubed. The right-hand side, again, I'm just going to write p of x times our 3x squared plus 3x squared y cubed. And then we have minus q of y times 2y. So it does not look like we can easily make a 2 appear from p of x times 3x squared plus 3x squared y cubed. However, we should be able to pretty easily translate that into negative 6x minus 6xy cubed. So we can use this component p of x times to create negative 6x minus 6xy cubed. And the way we can do that is we can use p of x equals 2 over x. Multiplying by 2 will raise everything to 6. We also just needed to drop, a negative 2 over x. Multiplying by negative 2 will give those negative 6s. And dividing through by x will drop our powers of x just as we needed. For our negative minus qy times 2y, we can use this to create our 2, our positive 2. So we're creating the 2 and then creating the minus 6x minus 6xy cubed here. So creating our plus 2, if we use q of y equals negative 1 over y, that will indeed become a positive 2. So now we can find capital P of x. So then mu of xy is equal to a capital P of x times capital Q of y, where capital P of x is e to the integral of negative 2 over x dx, and capital Q of y is e to the integral of negative 1 over y dy. So note, because I didn't really run through it earlier, this comes from doing using the fact that P of x is equal to capital P prime of x over lowercase p of x, assuming that mu takes that form. And so that will give us the capital P of x should be e to the integral of lowercase p of x dx. Same thing for the y. So if we do our solving here, we have p of x is equal to e to the negative 2 times the integral of 1 over x dx. So we get p of x is e to the negative 2 natural log absolute value of x. We can rewrite this as e to the natural log of 1 over x squared. And in other words, capital P of x is simply 1 over x squared. Similarly, capital Q of y is e to the negative integral 1 over y dy. Therefore, capital Q of y is e to the negative natural log absolute value of y. And we get, this is e to the natural log absolute value 1 over y. And we are just going to use then 1 over y as our function for cube of y. So what we wind up with then is our integrating factor is mu of xy is equal to 1 over x squared y. Okay. Right off the bat, I'm going to note the potential lost solutions. So mu of xy equaling 1 over x squared y. If x is equal to 0, this is always undefined, right? Or if y equals 0, then we get that mu is undefined from division by 0. Right? And so our potential lost solutions are x identically equal to 0 or y identically equal to 0. So this is just something to keep in mind. We'll check these at the end. Or we can check them, yeah, we'll check them at the end. All right, now let's go back to solving the problem. Let's multiply the original equation by the integrating factor. So let's multiply the original equation by mu. So our original equation was 2y dx plus 3x squared plus 3x squared y cubed dy equals 0. We'll multiply that entire thing by 1 over x squared y. In this dx component, 2y over x squared y will simplify nicely. So that will ultimately go to 2 over x squared dx. The second component, we will have a 3x squared over x squared y plus a 3x squared y cubed over x squared y dy. And then this is all equal to 0. Both of those will also simplify nicely. We will have 3 over y plus 3y squared dy, then equaling 0. So the x squareds cancel out. The over y stays in the first term, and dividing by y drops the power of y by 1 in the second term. Note, because the first component is solely in x, the second component is solely in y, when we go to take those mixed partials, we will just get 0 for both. We do have an exact equation. From here, we can go ahead and solve the exact equation. Doesn't matter which one we take, so let's use the fact that fx of xy is equal to 2 over x squared. Then we would get that f of xy is the integral of 2 over x squared dx. This becomes negative 2 over x plus psi of y. Then to solve for psi of y, if we take that partial with respect to y, this will be equal to psi prime of y, which should equal the dy component of our equation. So this should equal 3 over y plus 3y squared. If we go ahead then and take psi prime of y equal to 3 over y plus 3y squared, then we can find psi of y to be the integral of 3 over y plus 3y squared dy. So psi of y would be 3 times the natural log absolute value of y plus y cubed, technically plus c, but we only need one specific function. So then our solution, we know we have our general solution, f of x, y, set equal to c. So f of x, y is negative 2 over x plus our psi of y. So we have negative 2 over x plus 3 natural log absolute value of y plus y cubed. Set that equal to c. And then we have to also check our potential constant solutions. So we had x identically equal to 0 and y identically equal to 0. Let's start off with x identically equal to 0. Now that means x is equal to 0. It also means that we can view dx as equal to 0 since x is not changing. That also comes from dx dy, which is would be equal to 0. Right? And so we had 2y dx plus 3x squared plus 3x squared y cubed dy equaling 0. Dx is 0. 3x squared plus 3x squared y cubed would be 0. And so this does hold true. So x identically equal to 0 is a solution. Similarly, if we take y identically equal to 0, then dy is acting like 0. So we have 2y dx plus 3x squared plus 3x squared y cubed dy equaling 0. Here dy is acting like 0 and y is 0. And so both of these terms go to 0. And this is also a solution. So in this case, we have our general solution of -2/x plus 3 natural log absolute value of y plus y cubed equals c. And then we have the constant solutions on top of that, x identically equal to 0 and y identically equal to 0. Again, note in this case, we're viewing solutions either as the form y of x equals or x of y equals. Both are acceptable forms of solutions from the exact equation format.